Hi there, my name is Aaron Lanchman. I'm a professor of electrical and computer engineering at Georgia Tech, and I would like to welcome you to ECE3084 Signals and Systems. Suppose we're being visited by beings from another world, and their spaceship is shaped like a classic flying saucer. And I'm choosing a classic flying saucer because it's easy to draw, and I'm trying to draw something that's easy to draw because, as you can tell based on the radar dish I'm about to draw here, I'm not very good at drawing things. Anyway, what we would like to do is to figure out how far away the flying saucer is. A common way to do that is using radar, where we send electromagnetic radiation into the atmosphere. It will then contact the flying saucer, and then that radiation will be reflected back. And based on the time it took to go to the flying saucer and back, knowing what the speed of light is, which is roughly what the speed of the radar wave would be in our atmosphere, not exactly, but pretty close, we can then figure out how far away the flying saucer is, depending on that round trip time. And this object could be anything. It could be an airplane, it could be a car, whatever. This idea also applies to sonar, which might be used if you're, say, underwater and looking for submarines. Anyway, suppose for a second that the signal that is being sent, if I were to draw it as a function of time, looks something like this. Maybe it's like a triangle that starts at 0 and ends at 1. Now, generally, when I write an axis like this, there's an implied seconds. This would be something more like milliseconds or microseconds or whatever in practice. And I'm drawing the simple triangle just to have something easy to draw here. You wouldn't use this as a real radar waveform or even a real sonar waveform. And in any case, the actual waveform is usually best thought of as complex valued, but that's more complicated than I want to get into here. We'll talk about this a little bit later when we talk about baseband representations of bandpass signals, but that's something I want to talk about later. So I'm presenting an extremely overly simplified version of this idea. Anyway, if this is the function we're sending out in time, think for a moment about what this looks like in space. This part of the signal that's tall is going to be broadcast first, so it's going to come out. And so eventually we're going to have something like a waveform that looks like this in space. So down here, this horizontal axis represents a time coordinate. Here I'm representing a spatial coordinate. And as time moves along, this waveform is going to keep scooching along in space. So the waveform is going to hit the flying saucer, bounce off of it, and since the tall part of the signal hit it first, that's going to be what reflects off of the flying saucer first. So in space, the signal that looks like it's going back looks something like this. So it's going to fly back to the radar antenna, which now is acting as a receiver instead of a transmitter. And what are we going to receive? Well, it's going to receive that tall part first. However, it's going to be delayed by a certain amount of time. Maybe let's call it delta. And so the signal that's coming back will be going from delta to delta plus 1 in this example, whatever our time unit is. So up here, I was showing waveforms in space. Down here, I'm showing what they look like in time. So whatever the signal is, let's give it a name. We'll call it ST. And it can really be whatever. In a future lecture, we'll talk about how some choices of S are better or worse than others for different purposes. Now, what about the signal that we receive? Let me call it X. And it's going to be the signal that we transmitted delayed by a certain amount, delayed by this delta. And we never really receive this perfectly. This will usually be embedded in some noise having to do with background radiation and also noise generated in the electronics of the receiver, and maybe even quantization errors arising from the analog to digital conversion process. All of these things are fairly complicated, and to do a proper treatment of noise would take the development of a lot more mathematical machinery than I really want to get into in ECE3084. If you want to dig more into this, you can take ECE4260, which is Random Signals and Applications, or at the graduate level, you can take ECE6601, and we also have a class on radar signal processing. Anyway, here I'm just going to hand wave about the noise. Now, the name of the game here is to figure out what this delay delta was. So we're going to try to find delta, And what makes this tricky is that x is in fact embedded in this noise. So one approach is to try to guess what delta is and then see how close the shifted template, this S signal that I transmitted, is. And then if I think about the transmitted signal S as a template, I can ask the question, which delta out of a bunch of deltas that I can try gives us the closest match to X, the actual data I received. So let's try an approach that's sort of influenced by least squares methods. So what I'm going to do is say, we have some signal received, X of t, and let's guess a particular delta. And what I'm going to do here is I'm going to subtract the template shifted by that delta and then take the square of that difference. So this is an error metric at some particular time t. And what I would really need to do is to integrate over time. Now, of course, in any practical application, you wouldn't be integrating over all time. But I'm just writing stuff on the screen here, so I can integrate over all time. That's fine. Now, again, in a real radar application, these things would be complex valued, and you would take a magnitude squared instead of just a square, but we won't worry about that here. I can get the main ideas across here by leaving everything as real valued. So now that we have this, let's expand out this integral. I'll have x squared t minus 2xt s of t minus delta. And again, we don't really know what delta is. We'll have to basically compute this for a whole bunch of deltas. But something will come to our rescue that I'll show you later. And then so the last term, I'll have s squared t minus delta, all of this times dt. And so what we're going to do is we're going to try a bunch of deltas and pick the delta that minimizes this squared error metric that we've defined here. Now, something to notice is that this x squared t, it doesn't depend on delta. So we can actually leave it out of the computation if all we're trying to do is find a minimizer. And also this s squared t minus delta, well, if I think about integrating this quantity here, regardless of where I shift it to, the integral is going to be the same. It's just the integral of s squared t minus 3 is going to be the same as the integral s squared of t. So I might as well leave it out also. Okay, so I can get rid of this term, and I can get rid of this term, and I can scoosh over the integral and just put that minus sign out in front, and I can scoosh over the dt. And I should probably emphasize that for this equality to hold, I should really note that there are some constants here that we dropped, and these are constants relative to delta, which is what we're optimizing over. All right, so to match up with some traditional things, I'm going to make another change and change this minus to a plus. And now instead of picking a delta that minimizes a particular expression, we're really looking for something that maximizes that expression because I flipped the sign around. At this point, I feel like just making all of that other junk go away. And the last thing I can do here is saying, oh, if I'm maximizing this quantity, well, I don't really need the 2 here. Whatever delta maximizes it is still going to be the same thing. So I can actually get rid of the 2. All right, so let me recopy this whole mess up here. What we're computing is x of t, s of t minus delta dt, and we need to compute this for every possible delta, and we'll pick the delta that gives us the biggest number and declare that to be the round trip time to the target that we use to compute the round trip distance. And of course, this is all subject to noise and other effects that we have in the model, so you should never expect this to work perfectly, but it will get you in the ballpark. Okay, so now I'm about to do something that's super confusing, so watch closely. What I'm going to do is I'm going to take the delta here and replace it with t. Ah, you say, but I already am using t. I can't do that. Well, fear not. I'm going to replace t with tau. And this will seem extremely unmotivated until I show you what I'm up to here. So let's make those substitutions. I'll write this as x tau, s of tau minus t d tau. Oh, that looks an awful lot like something. It looks an awful lot like a convolution. However, a convolution didn't have tau minus t here. It had t minus tau. So let me try to write this a little closer to something that looks more like a convolution. So what I'll do is I'll take S, I'll put a minus here, and then I'll write t minus tau d tau. So these are equalities all the way through. So what do we have here? Well, this looks an awful lot like the convolution of x with s of minus t. So it's the convolution of x with a flipped version of s. Now, if we were to define a filter, ht, that was just s minus t, we can see that this whole operation is basically a filtering operation. We take our received signal x and we convolve it with ht. So I like this example of range finding as a motivation of the operation of convolution, and that convolution isn't just something that we use to describe and understand systems that nature gives us. It also describes something we might want to do on purpose. This particular ht, this is called a matched filter because it is a filter that is matched to the particular signal that you sent out into the universe. Now, in practice nowadays, most of these are implemented using digital techniques, but the underlying idea still applies. And when people are originally designing systems, they usually think about it in the continuous time domain first. Now, this operation up here, this looks an awful lot like convolution, but not quite. This operation itself has a name, and we call it cross-correlation. Now, unlike with convolution, where this asterisk notation is fairly standard in most engineering journal papers and in textbooks, there's not really a standard symbol for cross-correlation. So I've seen some books use kind of the 5-pointed star, and we actually used that for a while in 3084. But my colleague Chris Rozelle suggested that this is too easily confused with the 6-pointed star of the asterisks we use for convolution, and I agreed with him. And I've also seen a notation people use for cross-correlation where it's like this circle with a little X through it, but that's also used for a different thing in matrix algebra called a Kronecker product that also shows up a lot in quantum mechanics and quantum computing, which I've been looking at a lot lately, and so I find trying to use it for cross-correlation confusing as well. So the confusing notation that I'm ultimately adopted, that you will see in some papers and textbooks, is to use a giant letter R. I have no idea why people like to use a giant letter R. And what we'll do is we'll take this S function, whatever function is in that particular spot with this tau minus t, and write it first in the subscript. And whichever function has the tau, we'll write as an x here. And this whole thing is a function of t. So remember the part with the minus t here? That goes in front here. And now realizing that these things are equal, it's obvious that these things are equal. So a cross-correlation is just a convolution of a function with a mirror image version of the other function. So these are very closely related concepts. Now, something you have to be very, very careful with is that although convolution is commutative, meaning you can flip the order of the functions you're convolving, cross-correlation is not commutative. So in general, RSX does not equal RXS. And actually, that's difficult to say. So let me make one other tweak here. I know you're probably getting tired of tweaks. So here, all I've done is change the order of the factors in the integral, and I also replaced x with f. And the reason I did that is I would like to think about s as being the function that I slide, and f as being the function that stays fixed. And if we think about it like that, we can compute these cross-correlations using the sort of flipping and shifting idea that we used with convolution, except we don't actually do the flip. We just do the shift. Or if you want, you could just think about it as a flipping and shifting convolution where the thing you flip is a flipped version of one of the functions, which once you flip twice is the same as having never flipped at all. Yeah, it's confusing. Just deal with it. And once again, notice that in general, cross-correlation is not commutative. Because if I think about what this RFS is here, Now, of course, this would be f of minus t convolved with s of t, and these in general are not the same thing. Let me show you another way of writing this cross-correlation. Namely, let's do a substitution of variables. I'm going to write tau prime equal tau minus t. And if I do that, I can rewrite this autocorrelation as an integral of s tau prime. And then I'll have f. Okay, so let's see. What is tau? Tau is going to equal tau prime plus t. So I'll write tau prime plus t. And then the differential with respect to tau, I'll just replace that with d tau prime. And in terms of what's happening with the limits of the integral, well, I've got minus infinity or infinity shifted by something finite, so I can just leave the integration going from minus infinity to infinity. Now, this is actually the form of cross-correlation that you'll see most often in textbooks. I personally like this version better because it feels more obviously connected to convolution, but this is a perfectly valid expression for it. The way I like to think about this form is that you have some data that you've collected that is f, and then you're sliding the template along, marching it to the right as you're increasing t. Now, this version down here, what you essentially do is you keep the template that you're trying to match fixed, and you're taking the data you collected, and you're taking that whole data sequence f and sliding it to the left by t. So in one case, you're sliding the template to the right, in the other case, you're sliding the data to the left. Now, I've presented this material about cross-correlation from the standpoint of doing rangefinding as a way to motivate the operation of cross-correlation. Now, cross-correlation is a general operation that shows up in different contexts where S and F might represent different things. Similarly, when we introduced convolution, we motivated it from the standpoint of linear time invariant systems with a certain impulse response, and you could convolve the input with the impulse response to get the output. But that was just a motivational example in the way we tend to use the idea of convolution in this class. Convolution is a more general kind of mathematical operation. For instance, it shows up in probability theory if you have two independent random variables with different probability densities, and you want the probability density of the random variable that's the sum, well, you can convolve the individual probability densities. Let's return to the idea of matched filtering for a second. So earlier I said that we could define a matched filter that was just the flipped version of our template. Now, something might be bothering you about that. If you remember the original ST example I gave you, I had this little triangle kind of function that went from time equals 0 to time equal 1, whatever our time unit is. Now, if this is our S of t, what would our matched filter look like? Well, our h of t would look like a flipped version of this. So I would have something going from time minus 1 to 0. And this is problematic because if you remember, for a linear time invariant system to be causal, you can only have non-zero stuff to the right of 0. If you have any non-zero content to the left of 0 for t less than 0, then that filter is non-causal. It needs to be able to look into the future. Now, that's fine if you're processing data that was already stored on your hard drive, but in a real-time radar or sonar system, that wouldn't fly. Now, this isn't cause for too much alarm because you could create a new filter, say a causal filter, which is why I'm using the subscript C, where all you need to do is shift your basic matched filter over by however much time you need to in order to get everything on the right-hand side of 0. So if I were to shift this over by a time unit of 1, I'd wind up being okay. The thing you need to realize, though, is that all of your time estimates are going to be off by whatever that amount of shift was. And you need to compensate for that when you're actually doing the computation to figure out what the range is. The last thing I want to mention in this lecture is the concept of autocorrelation. And this is basically the correlation of a function with itself. And in particular, this kind of autocorrelation function tells you a lot about how good or bad a particular signal is in a radar or sonar kind of application. Now, this has a few interesting properties. One is that the autocorrelation itself is symmetric. That's not very difficult to prove. The other thing that's interesting about the autocorrelation is that its peak is at the origin. So RSS has a peak at 0. And if you think about it, it makes sense. The autocorrelation is sort of asking how much does the signal look like a shifted version of itself? And of course, it should most look like itself when you haven't shifted it at all. So if you compute the autocorrelation of a function and the peak's not at 0, you know you need to go back and double check your work. We'll look at some specific examples of autocorrelations in a future lecture.